So good morning everybody. Let's discuss the Hall watch and Lennard experiment. So it is comprising of a vacuum tube over here. In the vacuum tube there are emitter and collector, and this is a source of light. Photons are emitted on this and electrons are emitted from the metal. We have connected this vacuum tube uh, to a source of variable voltage through rheostat, and we have connected an emitter over here, which is a micro emitter basically. And this entire system is to make sure that we can vary the voltage and the various parameters concerned with the experiments. So there were certain results of this experimental setup which we are going to study. In all the results there is assumption that photoelectric effects takes place, so the constraints of energy, frequency and wavelength are satisfied. After that we got the results. The first result is that photocurrent under above conditions is directly proportional to the intensity, which is very obvious thing because intensity corresponds to the number of photons. So more the number of photons, more will be the number of photoelectrons, and it's gonna increase proportionally. Then we have another graph which is of intensity versus photocurrent, current versus voltage. So you can see that at zero voltage there is a finite current, obviously because electrons are being driven from energy of the light source. So that's why at zero voltage there is a circulation of electrons. Now if we increase voltage, then photocurrent increases up to a certain limit and then it becomes saturated, which is called the saturation current, which depends only on intensity but independent of frequency of light. This point should be remembered. Now if we reverse the voltage, then photocurrent decreases until it becomes zero at a certain negative voltage, which we call as the stopping potential, which is independent of intensity but dependent on frequency. And in this case we assume that the change in frequency is within 5% error, because intensity in general is also dependent on frequency. But in this case we assume that there is a variation of frequency within error limits of 5%. So we can assume that frequency practically remains the same, and it is the intensity or the number of photons which changes. So this graph is drawn under these conditions. Then we have the third graph in which we change the intensity at the same frequency. So if intensity is gonna change, then saturation current will increase. There are three different cases. So obviously intensity for case 1 is greater than that of 2, which is greater than that of 3. So which means that intensity of light corresponding to 1 is greatest. Whereas if you see the stopping potential is same for all, that means frequency will be same for all. So that is the analysis from this graph. Then we have another graph in which intensity remains same but frequency changes, which is shown by different stopping potentials. And as you can see that the graph corresponding to the largest magnitude of a stopping potential corresponds to the greatest frequency. So this graph we can analyze that as saturation current is same in all the three cases, so intensity is same in all the cases, and frequency is greatest for the third and least for the first. That is the analysis of this particular graph. Let's move further for the next graph, which is graph between kmx and frequency. So suppose there are two metals, metal A and metal B. Corresponding to graph A we have angle theta A, and corresponding to graph B we have angle theta B. So this angle corresponds to tan inverse h, which is constant for both of them. So we can say that theta is equals to theta B. Then from the graph we can analyze that frequency, threshold frequency corresponding to B is greater than that of A, which is quite shown by the graph here. And since threshold frequency of B is greater than that of A, so we can say that work function for B will be greater than that of A. And if work function is more, that means threshold wavelength will be less. So in this way we can analyze this. Now let's discuss another graph, which is graph between stopping potential and frequency. So Kmax is related to the stopping potential by the relation Kmax is equal to EVS. So the graph will be the same because they are proportional. Same means angles will be same. Threshold frequency for case B will be greater than that of case A, and threshold wavelength will be less than that of A. So both graphs will have same analysis patterns, and this is the analysis of the graphs related to Holboach and Lennard experiment. And as I have explained earlier, this experiment just put a question mark on the wave theory of light as put forward by Sir Huygens Christian, and it was the, you can say, the opportunity which made Albert Einstein famous. He published 3 research papers, out of which one was on photoelectric effect. So he got famous for this thing, and for this photoelectric effect explanation he got the Nobel Prize. So that is the potential of this experiment. Actually, Holboach and Lennard, they just performed the experiment and deduces some results on the basis of the experiments. Albert Einstein came into play when explanation was required that this is not explained by the wave theory. There were actually some problems related to this. The first problem was intensity problem, the second was frequency problem, and third was the time lag problem. As per the first problem is concerned, according to wave theory of light, intensity corresponds to the amplitude of electric fields, and electric field corresponds to the maximum kinetic energy of electrons. So larger the intensity means larger electric field, means larger kinetic energy. So that means kinetic energy should increase with intensity, or equivalently stopping potential should increase with intensity. But it was found experimentally that within error limits, Kmax, or stopping potential, is independent of intensity, but just depends on the frequency of photons. So that was the first problem. Second was frequency problem. So according to wave theory of light, energy of light is continuous. So any light of any frequency should be capable of providing enough energy to the electrons to come out of the metal and contribute in conduction. But when light is chosen such that its frequency is less than the threshold frequency, you keep on doing experiments for days or even weeks or even months, there is no photocurrent. So that was the second problem. The third was time lag problem. So according to wave theory, an electron should take a finite time, at least 2 hours, for an average intensity radiation to get enough energy to come out of the metal. But experimentally it was found that photoelectric effect is instantaneous. It takes a time less than 10 to the power minus 9 seconds as per given in NCERT. So these were the 3 problems, and these were explained using the concept of quantum theory of light, which we shall discuss in the next video. Thank you and have a nice day.